If neutrons are, say, disappearing, then maybe they are disappearing into an alternate parallel universe. Sounds crazy, but this is actual physics that people are testing. Imagine how different the world could be if parallel realities were not just confined to the realms of fiction. Would we be jumping between multiple dimensions like hopping on a train to go from one state to another? Do you think of each choice that you make possibly changing everything about the world that you exist in? It's not that your choices create different universes get created and maybe you're different in them. Well, the concept of different dimensions existing might not be fictional after all. CERN has just made a shocking discovery about the possibility of opening a portal to another dimension. How will this affect us? Is it even viable? Most importantly, are there any consequences to meddling with the fabric of space and time? Join us as we dive into CERN's spooky yet fascinating research. To get to the bottom of the whole deal with portals, dimensions, and particles, we first need to understand what CERN is and what it does. CERN, also known as the European Organization for Nuclear Research, is the product of scientific imagination nestled in the heart of Europe. This research facility has been in the picturesque countryside between the French and Swiss borders since the 1950s. Representatives from 12 European nations gathered in Paris to lay CERN's foundation with one goal in mind: creating a center for nuclear research that would propel Europe to the forefront of scientific discovery. Over the years, CERN has made significant contributions to the world, namely the World Wide Web in 1989 and the Large Hadron Collider (LHC) in 2008. The LHC was the world's most powerful particle accelerator, buried deep beneath the Earth, spanning over 17 miles in circumference, with equipment such as magnets, detectors, and experimental apparatus inside. The main point of CERN is to help us understand the universe around us in detail, and they do this by examining the smallest constituents of the universe, particles. With an array of particle accelerators and other machinery at their disposal, they plan to dig deep into fundamental physics. One such example of that machinery is the Large Hadron Collider, which is relevant to the topic of different dimensions yet to be explored. The Large Hadron Collider and the particle collision process raise many questions. So what is the Large Hadron Collider? Well, the LHC is the world's largest and highest energy particle collider. This spectacle of engineering is so awe-inspiring because it was built by the efforts of over 10,000 scientists and hundreds of universities as well as laboratories. It is hidden from sight at a depth of 175 meters (574 feet) within the Earth's surface and lies in a 27 kilometers tunnel near Geneva. The first collisions from the Large Hadron Collider were achieved at an energy of 3.5 to 5 tera-electron-volts TeV per beam in 2010. This amount of energy was worth noting because it was about 4 times the previous world record. However, the LHC has been shut down quite a few times for repairs and upgrades, namely between 2013 and 2015 and later in 2018, after which it was opened back up in April 2022. These frequent shutdowns resulted in the upgradation of the LHC from 3.5 TeV to 6.5 TeV per beam, keeping up with its status as a powerful particle accelerator and collider. 9 detectors and 4 crossing points allow the LHC to perform at the top of its game, detecting different phenomena around the crossing points. However, why are they even doing this? What need do we have to collide with particles and ions? The goal is to get answers to various questions. Where are the families of new particles predicted by supersymmetric theories? What do the particles do when they collide with each other at different speeds? How about the speed of light? What if there are new particles whose existence we are completely unaware of? All these unresolved questions in particle physics are the reasons why we built a facility as large as CERN in the first place. That brings us to the fascinating process of particle collision, something that has brought us infinitely closer to the possibility of other dimensions. The process of particle collision is quite possibly the simplest possible approach to studying the most fundamental pieces of our universe. In simple terms, we use such big machines to smash things together and see what happens. A very Neanderthal approach indeed, but it works. However, what sets us apart from Neanderthals is our tools and our approach. Instead of rocks and bones, we have accelerators that can make the particle speed approach the speed of light. In this multi-step process, the LHC consists of radio frequencies that accelerate charged particles to nearly the speed of light. They use superconducting magnets to maintain the circular orbit of these particles as their speed dramatically reaches 0.999999991 times the speed of light, only 3 meters per second shy of being the actual speed of light. The very first step is to inject the particles into something called a linear accelerator or LINAC. What it does is charge the particle to reach speeds of approximately 50 million electron volts. Then they are inserted into the circular accelerators, which gradually increase the energy of the particles to several trillion electron volts TeV. Some of these circular accelerators include the proton synchrotron booster, the proton synchrotron, and the super proton synchrotron. Finally, the two main rings of the LHC 27 km apart in circumference and 71.3166666666 magnetic fields energize the particles up to 7 TeV, and then the particles collide head-on from opposite directions. These high-energy collisions result in us noting some interesting things about the particles, whether it is new particles being formed or a blast of energy being released. These observations help us get closer and closer to understanding the universe around us. These collisions produce a wide array of particles, some that have never been seen before by any laboratory. How are these tiny particles observed? The detectors put in different places inside the collider track the paths of the charged particles and measure their energies, momentum and type. Analyzing these particle production patterns allows us to determine the properties of the detected particles and make further observations about their behavior. A question might arise in your mind: how do the particles in the LHC not miss each other during this particle collision process with a size so small? How do they move with such accuracy? Upon keen observation, it is noted that the particles in the LHC are bundled in needle-like packets, which are then squeezed to reach the collision point. Each needle-like packet is said to contain about 10–11 protons, with only a handful of collisions each time the two packets collide. Due to the frequent collisions, they can add up to billions per day. However, as marvelous as this creation is, there have been quite a few concerns about the LHC ever since it was created. The concerns about the Large Hadron Collider have been around for a long time, almost since the birth of the facility. Since its early stages, concerns about accidentally creating a black hole were raised, hypothesizing that it could devour our world. Recent discoveries by the Large Hadron Collider regarding the safety of the LHC have not stopped the clock of innovation and research, leading it to discover some amazing things. For example, physicists detected a mysterious primordial particle known as the X particle in early 2022. More specifically, it was X3872, first discovered in 2003 by the Japan-originated Bell experiment. In this experiment, the particle collider smashed together high-energy electrons and positrons to form the mysterious X particle, but they ended up decaying too quickly for any detailed examination. It was then proposed that X3872 would be better illuminated in quark-gluon plasma. Cut to 2022, about 100 of these X particles were detected inside a broth of quark-gluon plasma by smashing together lead ions. These particles were theorized to exist near the Big Bang for a very brief period of time. These findings were published on January 19 in the journal Physical Review Letters. Did you know that what we see in space, like planets, stars, and galaxies, is just a tiny part of the whole picture? In fact, it comes up to only about 4% of what's out there. What really defines the universe isn't so much the things we can see, but the empty space around them. Scientists have discovered that most of the universe is made up of things we can't see directly. These invisible substances don't emit light or any other kind of radiation that telescopes can detect. Instead, we can only detect them because of the way they affect the movement of stars and galaxies through gravity. We call these mysterious substances dark matter and dark energy. We're still not sure exactly what they are or how they've shaped the universe, but they open up exciting possibilities for discoveries in physics. Dark matter makes up about 23% of the universe. We first suspected its existence back in 1933 when we noticed that the way galaxies move suggested there was more stuff out there than we could see. We cannot directly see or interact with dark matter, but there are ways around this problem. Dark matter can be described as a murderer running away from a crime scene. The physicists survey the crime scene for bloody footprints, and these footprints give us hints and clues about how much of it is out there. So what could dark matter be made of? One idea is that it might be made of supersymmetric particles. These particles are like hidden partners to the particles we already know about, symmetrical yet opposite. Scientists are trying to find these particles in experiments like the ones happening at the Large Hadron Collider. Now let's talk about dark energy. Dark energy makes up about 73% of the universe. And it is believed to be causing the universe to expand faster and faster. Some scientists think dark energy might be related to empty space itself, while others propose that it could be due to a new force of nature. Whatever it is, scientists are still working hard to figure out how it works, how it affects galaxies, and what role it plays in the universe's evolution. There's a direct link between these ideas and the research conducted at CERN. Their quest to find the so-called God particle and dark matter particles often raises intriguing questions about the nature of our universe and beyond. But here comes the fun part. Physicists at CERN are theorizing that there might be dimensions beyond our regular 4-3 spatial dimensions plus time that we live in. CERN scientists propose that they might be able to generate phenomena that could reveal other dimensions. How? By smashing particles together with enormous amounts of energy, they create conditions similar to those in the early universe just after the Big Bang. At that point in time, physicists believe the dimensions we are familiar with may have been different. They think that other dimensions could affect the behavior of particles and lead to the creation of new particles that don't follow our known laws of physics. Imagine if we could find evidence of these other dimensions right here on Earth. CERN is leading the way with experiments designed to test theories of higher dimensions. In particular, they are investigating the possibility of microscopic black holes which might form if extra dimensions exist. If they can create and detect these black holes, it would provide strong evidence for the existence of extra dimensions. But be assured, if we ever succeed in creating a black hole, it would be microscopic and evaporate almost instantly due to quantum effects. This means that we're not in any danger of our planet being sucked into a massive void. Instead, the creation of microscopic black holes would offer a unique opportunity to study the behavior of gravity in different dimensions, helping to unravel the mysteries of our universe. Many theorists have suggested that there may be other dimensions beyond the ones we are aware of. Some of these theories include the string theory, where the universe is made up of tiny strings vibrating at different frequencies. These strings could create particles that manifest in our world. Imagine a universe composed of multiple strings. Each string could create a different reality depending on its vibration. This is a mind-boggling concept, isn't it? The implications of other dimensions are staggering. If we could access them, we might find new technologies, advanced civilizations, and even new physical laws. Could we interact with other versions of ourselves? What might that mean for our understanding of identity and existence? In short, CERN's ongoing research may unlock some of the greatest mysteries of our universe while simultaneously igniting a plethora of ethical and philosophical debates. As we stand on the brink of scientific discovery, it's crucial to remember that with great power comes great responsibility. So what does the future hold? Only time will tell.